All right. Okay, guys, let's continue. Now, after chapter 5, chapter 6, chapter 7, and chapter 8, I will try to cover these 3 chapters as much as possible. Chapter 6 is series solutions of linear equations, and chapter 7, as you know, it is Laplace transformation. So in this chapter, we'll talk about 4 things. Number 1 is preliminary theory, that is linear equations. No, wait. Where did I get this? It is chapter 6. Okay. All right. Just give me a minute. Review of our series. That is the first thing we are going to talk about in this chapter. The second one is solutions about ordinary points. And third one is solutions about singular points. And the special functions. Linear equations. Okay. I don't know why I made this mistake. Anyway, so here we have 4 subchapters. The first one is a review of power series. That is, you learn, actually are supposed to learn this in Calculus 2, right, or Calculus 3. Before, actually, I used to teach this in Calculus 2. In Thomas Calculus, that is in chapter 10. And I will do some revision for you, but if it is not clear enough for you, I suggest you to open the chapter 10 from Thomas Calculus. Just review a few things. Number 1 is what is power series, and what we mean by it is convergence and divergence, okay, and the things. And the second one is solutions about ordinary points, solutions about singular points, special functions. And I will say, maybe I'm thinking to teach you only 6.1 and 6.2. Solutions about singular points, we will see. Special functions also, I will say, maybe I'll just introduce and skip this because I'll try to give you some general idea about the chapter. Okay, series solutions. What we mean by this series solutions of linear equations, and how do we find a series solutions of linear equations. Once you get this general idea, and after that, the mathematical part is similar, just you need to get some, how to say, be familiar with some definitions about singular point, what we mean by this, and after that, the procedure is the same. And also special functions, I will say, okay, maybe I'll just introduce with some of them, and I will skip this. Actually, I'm skipping, not because they are less important, they're also very important, but they are not very important to learn chapter 7 and 8, okay? In general, actually, they have a lot of applications, especially the special function, we have a few functions there, okay? But you can study and learn by yourself. All right. So that is, up to this point in our study of differential equations, we have primarily solved linear equations of order 2 or higher that have constant coefficients, right? In chapter 3 and 4, what we did is we just considered a few different methods, right? We learned a few different methods, and all methods is about solving linear differential equations where coefficients were constant. And when coefficients were not constant, we only actually solve one case, right? That is Cauchy-Euler equation, right? And using that variation of parameters, using that method, we solve only a very specific example. But in general, the methods that we have learned so far, it does not work up to some equations. For example, let's say, for example, that here y double prime plus xy is equal to 0. Okay, it looks very simple, right? It's the second order, but is it linear? Yes, linear, right? Because y or y prime is not multiplied by y or itself, right? We do not have here y times y prime, or we do not have here y prime squared, so that is linear. At the same time, it is homogeneous, right? But if you try to solve this one, you cannot solve this by using the methods that we have learned. It looks very simple, but try this. We cannot do this. Okay, and then also second example is similar. Anyway, so here in this chapter, it doesn't mean that okay, we cannot solve this. The method that we have learned, it does not work for this method. Should we just stop doing our research or studying? No. So mathematicians actually studied on these kind of equations, and actually they developed the technique of what is it? Series solutions of this kind of differential equations. Okay, but still you will see that we will be able to get two linearly independent solutions. So we will have two solutions. Here we will have one solution, y sub 1, second solution, y sub 2, and these are actually found by using power series solutions. That means that y1 will be equal to the polynomial here on the right hand side, but it has infinitely many terms. Also y sub 2 is the same thing, and after that the linear combination that y of x is equal to c sub 1 y sub 1 plus c sub 2 y sub 2. It gives us the general solution of this equation. But once again, here, this is not the function that has finitely many terms. Okay. A series means it has infinitely many terms. Okay. All right. So in this chapter, we will study two infinite series methods for finding solutions of homogeneous linear second order differential equations. The homogeneous linear second order differential equations. Right? And here we have a sub 2 of x, y double prime, plus a sub 1 of x, y prime, plus a sub 0 of x, y is equal to 0, where the variable coefficients a sub 2, a sub 1, and a sub 0 are, for the most part, simple polynomial functions. Simple means maybe it's just x or x plus 1 or x squared, something like this. Okay, simple polynomial functions. Okay. And also why you may wonder why always you're talking about the second order, because it has a lot of application, okay, in physics, in science in general, and that's why they spend a lot of time on the second order differential equations. Anyway, so again, as review material, what you have to know to study this chapter is you need to review infinite series of constants like P series. Infinite series of constants means what are the series like 1 plus 2 plus 3 plus 4 plus till infinity. This is one example for infinite series of constants. And P series, okay, we just write P series, you can search in Google or again in chapter 10. Just have a look, get some idea, that much is enough. Harmonic series, that harmonic series is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 for infinity. Alternating harmonic series, alternating means here the first term is positive, the second term is negative, third term is positive, negative, change actual alters like this. We call this alternating harmonic series. And harmonic here means that is for alternating harmonic series, we mean this 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 is minus dot 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 until geometric series. You should know actually about geometric series. Test for convergence, especially the ratio root test. Now we will talk about this a bit later. Second thing is that you have to know power series, okay, Taylor series, Maclaurin series. Here we are going to review this, but if you want to learn more, if you forgot a lot of things about this, I suggest you to open the chapter 10 in Thomas Calculus and have a look, see one or two examples. That will be enough to study this chapter. Okay. All right. Now let's move to our revision part. Power series. I think today mainly we will do some revision. Okay, we will see maybe 2-3 examples, and next time we will do some more examples. At the beginning, let me tell you, when we just try to find this power series solutions, you will see that even the simple question that y double prime plus x times y is equal to 0. Okay, to solve this question, you will see that you need to go through a lot of steps. It is not, I mean, the solutions are not very short. Okay, first you need to convince that you're going to through a lot of long steps. But don't be lazy to write every step, especially for the first 1 or 2 examples. If possible, write every term. At least if you're writing the polynomial series, write at least 4 or 5 terms, and just see what's going on there. Okay. Anyway, so what do you mean by power series? Power series in x minus a. Power series in x, power series in x plus a, power series in x minus a is an infinite series. So infinite series means the sum of infinite terms of a sequence of numbers, right? Or something, anything. So here we have, this is how we define power series, the sigma notation. That means it is sum, right? N change from 0 to infinity. C sub n, that is a coefficient. X minus a to the power n. X to the power something, that's why it is called power series. And if you just expand this, what do we get here? If n equals 0, substitute here 0. So here we have C sub 0, right? Because n equals 0. Okay, plus next index, n equals 1. If n equals 1, here we have 1 x minus a to the power 1. So here we have C sub 1 times x minus a, right? Okay, go back. N equals 2 now. If n equals 2, here we have 2x minus a squared. So C sub 2x minus a squared. And once you see the pattern, then we can just stop. Just put dot, dot, dot. Now we can see the pattern here, right? How about if I write nth term? That means that when n equals n, C sub n, right? X minus a to the power n. This is the nth term. And plus, it continues because it goes to infinity. Right? So such a series is also said to be a power series centered at A. Okay, centered at A. Why it is centered at A? Because when we talk about power series, actually, here we talk about power series representation of some functions, especially non-elementary functions. Sometimes you will see that, for example, sine x squared, right? For example, or what is it? 1 over natural logarithm of x. Some non-elementary functions. When we just represent them in power series, it is easy to deal with this power series, right? I can differentiate this, I can integrate this easily, or I can evaluate approximate value of this function. If I just write here, let's say that is power series representation of some function here, f of x, right? It's just a polynomial. Yeah, it goes to infinity, but I don't have to pick all the terms here. So maybe I can get like the first 10 or the first 50 or the first 100. That gives us sufficient, how to say, the approximate value of this function. For example, if you're interested to evaluate this value at certain points, right? So maybe this function is really complicated to evaluate. And after that, using this polynomial power series representation, we can evaluate or deal with this function. So some examples for power series in x minus a. Here, for example, the first example, that is one example, x plus 1 to the power n. So what is a here? A is equal to -1, right? So that thing is centered at -1. What does it mean? It means that assume that this is the power series representation of, let's say, some function f of x, right? And it is centered at -1 because at -1, this thing is equal to 0. So if I just draw our coordinate system, so that is x-axis, this one is y-axis, -1 is here, okay, -1 is here. And let's say this power function, this function, its graph is something like this. Okay, something like this. Maybe this part, I don't have to draw this. Draw shorts. something like this. Hmm? Let's say something like this. Okay. And centered at A, but here centered at -1. What do we mean by this? Here, our function is given, right? Some kind of complicated function. So that is power series representation of this function, right? If I just write a few terms of this function here, when n equals 0, for example, here f of x is represented by this power series, right? If n equals 0, it is 0. Here we have 1. Plus, if n equals 1, here we have x plus 1. Plus, if n equals 2, here we have n plus 1 squared. 3, n plus 1, 3. Dot, dot, dot. Continues, right? So actually, if I just write only one term, right? Approximating this function with only one this. Okay, here we have this point, right? And it is here we have 1. Something like this. This is 1. I'm approximating the value of this function with this line, right? How close they are? Do they look like each other? No, it's just a straight line, but this is a curve. But if you just approximate the value of the function very near to -1, and also these values, right, they are very close to each other, right? But how about if I just add one more term now? Not instead of 1, but I'm going to approximate with this 2. So that is x plus 2, right? What is x plus 2? X plus 2 is something like this, straight line, again. And it gives us better approximation, right? And how about if I take 3 terms here? Now, if you just take 3 terms, what we have here? Here we have x plus and something, right? Here we have quadratic function, right? So if you just say quadratic function here, maybe it gives us something like this. Okay. But how about if you add one more term? Now here we have cubic function. We know the cubic function is graphic. Graph is something like this now. It's something like this. You see here, it gives better approximation. If you add one more, maybe it gives us something like this. As you add more and more terms, it gives us better and better approximation of this function near this point. How about if you get all the terms, actually it gives us the exact value of this function if you are able to evaluate this. Okay, so that is all about this power series representation. Okay, and a lot of times, for example, we have some functions, it's not easy to deal with, so you just express them in power series representation. Another example is, for example, here we have another power series representation of different function, 2 to the power n, x to the power n, right? And start from 0 to positive infinity. As you see here, we have polynomial function here. Just x, the powers of x, multiplied by constant. So here we have 1. When n equals 0, here we have 1, right? If n equals 1, 2x. If n equals 2, 4x squared. If it is 3, 8x cubed. If it is 4, 16x to the power 4, something like this. It's just some examples for power series. Some important facts to know about power series. So the following bulleted list summarizes some important facts about power series. Again, what we are talking about this series, right? That is n change from 0 to positive infinity, c sub n, x minus n to the power n. The first thing is convergence. Okay, convergent or divergent, because mainly we are interested in convergent power series. Okay, a power series is convergent at a specified value of x, at any point of x, if a sequence of partial sums, the partial sums converge. That is, limit when n goes to positive infinity, this s sub n of x, which is equal to this, it must exist. And also from calculus, you know what we mean by this, right? It must exist means this limit, we should be able to calculate this. When you evaluate this limit, it must approach to something. Since here we have x, for example, it must approach to like some kind of function, maybe this x, maybe x squared or something. It is not or is it? It's not. It does not going to. What is it? So it is possible to avoid this limit, and it does not go to. It does not go to positive infinity or negative infinity or something. Um, okay. So by this, we mean that as you add this partial sum, right, s sub n of x, just one example is, let's say our power series is 1 plus x squared plus x to the power n continuous, right? This partial sum is s sub capital N of x. What is it? That's equal to 1 plus x plus dot 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 plus x to the power n, right? Finite number of terms. So now if I evaluate this, I will get something here, right? Because just a geometric progression, right? It has n terms. I can evaluate this, right? If I evaluate this, we get something or some kind of expression in terms of x. And we need to evaluate this limits. When n goes to positive infinity, can you evaluate this limit? Does it exist or not? Okay. If it exists, we say that it is convergent. If it does not, it is divergent. Okay. Usually, we just need the functions which are convergent. We have nothing to do with divergent functions, right? Convergent means that we can approximate the value of the function, which is represented by power series. We will see this in example soon. So interval of convergence, second thing we have to know. The first one is we have to determine, or we should know how to determine either the given series is convergent or divergent. Second one is, okay, let's say it is convergent. Next question is, okay, it is convergent where? Or at what values of x the function is convergent. So interval convergence, every power series has an interval convergence. So interval of convergence is the set of all real numbers x for which the series converges. Okay, the center of the interval of convergence is the center A of the series. All right. And also example, in the previous example, when we're talking about some function, it has power series representation. The center was -1, right? That is our function. Okay. So there must be some interval. Sometimes it is infinite or finite. Okay. In certain interval, the function is convergent. If you just go out of this interval, take any value, it may not be convergent. Okay. It depends again on the type of the function. For some functions, they're always convergent for every value of x on the number line. For some functions, only a certain interval, like for example, tangent inverse of x, that is only convergent between on the interval from -1 to 1. Okay. And radius of convergence. The radius r of the interval of convergence of a power series is called, it is radius of convergence. If r is positive, then a power series converges for x minus a less than r. Okay. And diverges where x minus a is greater than r. It has absolute value. Again, what do we mean by this? Here we have a, right? That is the center of convergence, right? And this x minus a, absolute value of x minus a is less than r, means that this x minus a, right? This x minus a is greater than -r and less than r, right? So that means that here we have a minus capital R less than x less than a plus capital R, right? So here we have a. What is a minus r? It is somewhere here. That is a minus r. Here r is positive. A plus r, it is somewhere here, right? So that this a is in the center. Okay, that's what is called center of convergence. and all the numbers between a minus r and a plus r, right? These are the points where the function is convergent at. And that's why this r is called the radius of convergence. It is symmetric. Usually it's always symmetric. Okay. So if the series converges only at its center A, if the series converges only at one point, right, then radius is equal to 0, because a plus 0, a minus 0. If the series converges for all x, then we write r equals positive infinity. Okay. It means that, like, for example, you will see that in the next example, sine of x. And power series represented sine of x is something, right? And the interval of convergence of sine of x is the whole number line. So that the radius of convergence is positive infinity. Okay. Absolute convergence. Within its interval of convergence, a power series converges absolutely. What does it mean? It means that, again, if you're talking about some power series and power series converge absolutely, means here we are talking about this power series. N equals 0 to positive infinity. Here we have c sub n, x plus a, or x minus a, doesn't matter, to the power n, right? That's our power series. So within its interval convergence, so we just found out that this R, let's say it is something 2 or 3, anything. Okay, the center convergence is 0. So our function is, the power series is convergent on the interval from -2 to 2. Okay, so for every value, it is convergent, right? It's saying that within its interval of convergence, a power series converges absolutely. And also, if we just take absolute value of every term, we form new power series, right? Also, it will be convergent. Actually, that's a theorem. Okay, that means that also if this absolute value or this series, right, converges absolutely, and also actually the given power series will be convergent. Here actually we are talking about this number line. That is a center of convergence, and that is a radius, right? Here, if you just pick any value from here and put in the power series, right, and evaluate this, it will be convergent. And if you just go outside this interval, it is divergent. And the question is, how about that at this endpoint? And it depends on the function. We are not sure. And sometimes it's convergent, sometimes it's divergent, and sometimes here it is on the left, it is divergent, here it is convergent. Okay. Anyway, that is one convergence test, ratio test. We have a few other tests, but mainly we are going to use this one. If you just get some idea, that is enough. After all, it's just a revision. Convergence of power series can often be determined by the ratio test. What is ratio test? Suppose the c sub n is not equal to 0 for all n. Okay, we are talking about this power series. Okay, and we want to determine, is it convergent or not? Okay, and ratio test says that if, let me just write this thing, sigma n equals 0 to positive infinity, c sub n, x minus a to the power n, right? If it is 0, here we have 1, here we have sub-0. Plus dot 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 continue. If is equal to n, here we have c sub n, x minus a to the power n. Next term is c sub n plus 1, x minus a to the power n plus 1, and continues, right? This ratio test says that in order to determine the given power series, either it is convergent or divergent. Okay, take this n plus 1's term, this one is n plus 1's, right, term, and the ratio of this to this, the previous term, that is n's term, that is n plus 1's term, n's term. Okay, evaluate this. Okay, and evaluate the limit of this ratio. But first, if we substitute here, we have c sub n plus 1, x sub minus a to the power n plus 1, c sub n, x minus a to the power n. So they cancel out each other, right? So this x minus a, I can take this out because it has nothing to do with this n. It's not dependent on n. Instead, what we have here, c sub n plus 1 and c sub n. Let's say when you evaluate this, we get this L. Okay, something else. So it says that if L is less than 0, then the series converges absolutely. Okay. If L is greater than 1, the series diverges. If this L is greater than 1, it diverges. If L is equal to 1, the test is inconclusive. The test is inconclusive means we cannot say either it is convergent or divergent. So how can we determine that? Then actually we need to use different methods. Maybe root tests or maybe other methods. Okay. So this method does not give us any conclusion. Okay. That is just one ratio test. Let's say one example, and after that you'll have break. Interval of convergence. Find the interval and radius of the convergence for this. Okay. Now I can just write this power series. Right? And number one is first interval and radius of convergence. First, we need to find when this power series is convergent. So I'm going to use ratio test here. Here we have a sub n plus 1, that is n plus 1's term, that's equal to x minus 3 to the power n plus 1 over, here we have 2 to the power n plus 1 times n plus 1, right? And how about a sub n? N's term is just equal to x minus 3 to the power n over 2 to the power n times n. First, let me just simplify this. Then I will evaluate its limits. So what is a sub n plus 1 over a sub n, right? That's equal to this, x minus 3 to the power n plus 1 over 2 to the power n plus 1 times n plus 1. When you divide this, I should just write this upside down. Here we have times 2 to the power n times n. Here we have x minus 3 to the power n. Right? So if you simplify this, 2 to the power n, 2 to the power n is gone. So here we have 1 over 2, right? Because here we have 2 to the power 1. And n over n plus 1, we have nothing to do. So here we have n over n plus 1 times x to the power n plus 1, x to the power x minus 3 to the power n. So here we have x minus 3, right? So now if I just evaluate its limits when n goes to positive infinity, here we have absolute value of a sub n plus 1 over a sub n. These are not the coefficients. These are n's and n plus 1's term of this power series, right? And I have already evaluated this 1 over just constant. I can take this out using the limit property, x minus 3. Also, it has nothing to do with this m. So here we have absolute value of absolute value of x minus 3 over, here we have 2 times limit as n goes to positive infinity. Here we have n over n plus 1, right? And you know how to evaluate this limit. If you just divide numerator and denominator by n, here we have 1 over 1 plus 1 over n. When n goes to positive infinity, this limit exists. That is equal to 1 over 2 times x minus 3, right? That is the second step, actually. Now, using the ratio test, it says that for this power series to be convergent, this should be less than 1, right? So this is convergent, number 3, to find the interval and radius of convergence when it is convergent. This should be less than 1. So here we have x minus 3, x minus 3 over here we have 2. This should be less than 1. Otherwise, it is not convergent, it's divergent, right? So here, if we just solve this, here we have x minus 3 less than 2, right? From here we have x, add 3, here we have 5, right? Negative 2, add 3, it is 1, right? So here, this is the interval of convergence, right? So here, 1 to 5, if we just pick any value from this interval, right, and substitute here, we will get a series, right? All the terms are constant. If you just add this, as you add more and more and more terms, it always approaches a single value, right? The convergence means this. And how about the radius of convergence? Here, x minus 3 less than 2. So the radius of convergence is equal to what? It is 2. And how about the center? Here, the center is 3, right? That is how we determine the interval of convergence, radius of convergence, and also determine either the given power series is convergent. Okay. All right, guys, it's about 1 minute left. Let's have break. And if you did not understand anything, we can have some discussion before we start the second session. All right. 10-minute break. See you after 10 minutes.